everybody, and welcome to our first video for AP Chemistry in Unit 1. So this video is going to cover, it looks like pages 2 and 3 in the notes for today. And this video is all about mass spectrometry or mass spectroscopy. From what I understand, they're basically the same thing. I think one's more of an umbrella term for the other one. So mass spectrometry, what is it? This technique allows chemists to determine the masses of elements and their isotopes. So you might not have thought this before, but iron's atomic mass on the periodic table is a specific value. And how do we know that value on the periodic table? You might remember from Chem 1, we needed to determine all of the percentage of all of the isotopes of that particular element of iron. But how do we know what they are? And chemists can do that using mass spectrometry. And rather than write on here for the words, I'm just going to type it out just because I think it would make it easier for you to read, and it's a lot faster for me as well. So mass spectrometry is an analytical technique that's used to determine the atomic mass of elements. So it's an analytical technique that's used to determine the atomic mass of elements. If you take any sort of a chemistry class in college, you'll definitely use a mass spectrometer. I believe I used a mass spec when I was in organic chemistry, so you'll definitely use one there. And we can determine the atomic mass of elements, of course, using a mass spectrometer. So a mass spectrometer is the most accurate instrument currently available to determine the mass of an element's isotopes. And remember, an isotope of something is, so if I have the same element, but they have, because they're the same element, they have the same number of protons, but they have a different number of neutrons. And you don't have to write that out as intense as I did there, but again, I'm going to type it out there. I think it's faster for me. The video will be a little bit shorter, and it's easier for you to read afterwards. So chemists do that using a mass spectrometer. And I'm going to explain to you how a mass spectrometer works. You don't have to know how it works, but it's pretty neat, actually, how this happens. I'm going to start writing here just because it will be easier for me on this image right here. So what we do right here is, this would be an example of an instrument of a mass spectrometer, right? So here is the whole entire thing right here. And this instrument is going to tell us what is the mass of ions in a particular sample. So what we're going to do is we're going to inject the sample right here. So typically you'd have some sort of a little syringe right there, and we'd inject our sample. So we inject a sample. And that sample is just going to contain a whole bunch of isotopes of one element, right? And we have to first make each of these particular elements into their ions, because that's really how this works right here. So I have this thing right here, and this ion source is going to eject electrons from the sample. Remember, you don't really need to know this, but it's kind of cool to understand how it works. So that pulls electrons away from the sample in order to make ions. Those ions run through this mass filter, right? Or this basically a giant magnet. And right here, when we inject that sample, all of those are going to have the same affinity, I guess, is what we could say. But Because they have different masses, we have to separate those isotopes based on their masses. And we do that using a giant magnet. And that's what this is right here. So once it enters this magnet right here, it's going to go around this curve right there. And this analyzer, so we could say mass filter / analyzer, is going to separate these different isotopes based on their mass. So the ones up here towards the top might be the heavier isotopes in that particular sample, and these would be the lighter isotopes in that sample. And what we would produce is something that looks like this. This is really the most important thing that we would get from that. So all of that jargon basically produces this. So let's say that we actually use this for a sample of neon. So I would inject neon into this ion or into this mass spectrometer. Electrons would be pulled away from those neon atoms in order to create ions. Those ions would then go into this analyzer and be separated based on their mass. And we would produce some sort of a spectrum through this detector. So in this case, it looks like most of this sample has a mass of 20, right? So most of this sample is going to be neon 20. And in fact, this is present in about 90.92%. And we could tell because this peak is very, very high. So most of this sample contains neon 20. A much smaller percentage is neon 21. And we could see that this is giving us the actual percentage value here, but 0.26% is neon 21. And 8.82% is neon 22. And we could see that from this much smaller peak. It looks like there is no neon 19 and there is no neon 23. So this particular spectrum is telling us what percentage of each isotope is present in an element. So for neon, it looks like there are 3 different isotopes of neon having a mass of 20, 21, and 22. And it's really cool how that works, actually. This is a very complex instrument. You don't have to know how this works, but I just like to show you where we're getting that particular spectrum from. And it's because a magnet is separating each of those masses. And here's just another sample of what this would look like. We have down here the mass number, which of course is going to be just the mass of the sample. And ion beam intensity. So this particular sample is not showing us exact percentages, but that's okay because we could still clearly see that the highest percentage of this would be neon 20. So the smallest percentage is neon 21, and somewhere in the middle is neon, not in the middle, a little bit higher than 21 is 22. A lot of times you're going to see this right here. This is the most common representation right here. So most common representation. You're going to have a bar graph of sorts. And a lot of times the bar graph will tell you the percentages here. Sometimes they don't, but you could estimate approximately the percentage there. So 91% of this is neon 20, 0.3% of this is neon 21, and 9% of this is neon 22. Now, if you remember back to Chem 1, using those percentages, we can determine what's the atomic weight of an element. So we can look at neon's atomic mass on the periodic table, its molar mass, and that molar mass does not match 20, 21, or 22. It's going to be a little bit different from that. And that's where you use these percentages, multiply it by the mass in order to get the mass of that element, which is actually what we're going to do here, just to refresh your memory. So let's go ahead and try sample problem 1. When a sample of natural copper is vaporized and injected into a mass spectrometer, the results shown to the right are obtained. Use this data to calculate the average atomic mass of natural copper. The masses are 62.93 atomic mass units and 64.93 atomic mass units. Average atomic mass of natural copper. This is the value that we find on the periodic table. So why does the periodic table have a mass different from these mass numbers that are given to us in a mass spectrometer? This is why. There are a couple of different steps how to do this. What I like to do first, though, is to just kind of organize my data. So I have copper 63 and I have copper 65. So I'm just going to list right there my two isotopes that I'm working with. I'm going to look at this mass spectrum first. And remember, these values that are given to me are the percentages of each isotope. I'm going to start off with those first. And I'm going to identify, so 63 goes to the 69.09%, and the 65 goes to the 30.91%. I want to get these out of percents. So the first step is to divide by 100. And you don't have to write this step out like I am here, but I'm just kind of in that zone. I've been doing this for a long time. 0.6909. So I just divided both of these percents by 100 just to get it to its fraction form. Then I'm going to take that and I'm going to multiply it by the mass of that particular isotope. So I'm going to multiply this 0.6909 by the atomic mass of copper 63. And it's telling me here that copper 63 has an exact mass of 62.93 AMU. Why is it not exactly 63? Well, that's because protons and neutrons don't weigh exactly one atomic mass unit each. They're a little bit less than that. So I'm going to multiply this by 62.93 atomic mass units. And I'm going to multiply this bottom one by the 64. 64.93 atomic mass units. And when I do that, I'm going to get two different values. So the top value that I get is 43.48 atomic mass units. See how it's easier if I if I type things out. Sometimes it's a little sloppy to read when I'm writing. And this bottom value is 20.07 atomic mass units. Last step is going to be to add them up. So when I add together 43.48 to 20.07, I get 63.55 atomic mass units. So that means that on average, one atom of copper has a mass of 63.55 atomic mass units. Notice it's a little bit closer to 63, and that's because there is a much higher percentage of copper 63 in a given sample. 69% of copper is going to be copper 63. So of course the average mass of a sample, even if I have 100 grams in my hand, on average, every single atom has a mass of 63.55 atomic mass units. It's very difficult for chemists to isolate singular atoms, so we have to use a weighted average considering the percent abundances in order to determine, okay, well, what's the mass of a single atom? So knowing that we have copper 63 in much higher abundance, that atomic weight is going to be, or average atomic mass is going to be much closer to 63, which we see here. This is the value that you find on the periodic table. So if you look on a periodic table right now, you will see that the value that is listed is 63.55. And that's because chemists have already considered these mass spectrums and did this particular work in order to figure them out. Notice there is no 64. That's because copper is not prevalent in having a mass number of 64. But that's how you would do that. And it's really that general process for each of these. So let's try this one down here. An element X has 5 major isotopes and are listed with their abundances below. What is the element? Does the atomic mass that you calculated agree with the periodic table? So I'm not going to draw this out for you explicitly. I'm not going to go through this in the video, but I will tell you steps on how to do this. So like I said, first things first, I just like to list each of my isotopes here. So I have 47, 48, 49. So we're trying to identify what is X here. And I'm just going to list these percent abundances, and then I'm going to divide them by 100. So I'm going to do that off screen, and you can just do that yourself here. Okay, so there's this first part done. Notice how I did keep my significant figures. You do want to try to be as precise as the least precise value. So every one of those values does in fact adhere to significant figure rules. Now that I've got it out of that percentage form, I'm just going to multiply each of these values by its appropriate atomic mass. So for this first one, I'm just going to multiply that by 45.95269 AMU. And I'm going to get some value. So I'm going to do this for the rest of these, and you can do the same. And there's that next part there. Notice how the largest value of masses for that step corresponds to 48X, so the isotope of X that has a mass number of 48. And that makes sense because that isotope is present in 73.8% abundance. So the mass is going to be the greatest from that. The total molar mass is going to come the most from this particular isotope because this is the highest in abundance. And then the last step is to add them up. So if I add all of these up, I get a value of 47.9 atomic mass units. And that particular value corresponds the closest to titanium. So if you look on your periodic table, you would see titanium is the value that's the closest. Scandium's at about 44.96, vanadium's at 50.94. So it's definitely closest to titanium. Not exact. This periodic table that I'm looking at says the actual value is 47.867 atomic mass units. And of course, we don't have as many significant figures as that because our percent abundances weren't that precise. They only have one place after the decimal. So let's see, what is the element? We just did that part there. And it says, does the atomic mass that you calculated agree with the periodic table? Let's go ahead and insert a text box here just because it will be easier for me to type this out from before. Okay, spinning wheel of death. There we go. Let's go ahead and insert some text here. So we'll do this red and bold. We'll say yes, it does. But we'll say the calculated value is slightly off from the periodic table. Probably due to a lack of precision in the percent abundances. And that's due to too little sig figs. Sig figs will always come back to haunt you. So, yes, this atomic mass does agree with the periodic table, but it's a little off, and probably because we don't have very many significant figures in those percent abundances. And that will conclude this first video all about mass spectrometry. We're going to work a lot with this kind of stuff in class. not just this particular way, but I'm going to work you through some other problems in class as well, kind of looking at graphs and determining what would be the most percent or the most abundant isotope for that particular element. Ask me any questions you have in class, and I will see you in the next video. Bye.